Alright, ladies and gents, we're in Unit 9 in Calc BC, or Calc 2, and we're going to be talking about sequences and series in this whole unit. And this whole unit is really long because this is all brand new material for the most part. You did a little bit of sequences, maybe in series, like arithmetic series and geometric series in pre-calc maybe, but for the most part, this is probably new material. So we're going to start very easy with 9.1, and we're going to get just in the basic, ooh, that's yellow, I don't want yellow. My daughter was playing with this one. So we're going to start with basic sequences, and we're going to get harder from here. So mathematically, sequence is defined as a function whose domain is the set of positive integers. So positive integers, remember, are just like 1, 2, 3, 4, right, and so on. And then each of those numbers, so you have them right here, are mapped to a specific value. And this is like your y value, if you think about it. Like you put the 1 in and you get something out. You put the 2 in and you get something out. And you put the 3 in, you shake it all around, you do the hokey pokey, and you get the 8 of the third thing out. And the A1, A2, A3, or A sub 1, A sub 2, A sub 3, I guess maybe I should say it properly. They're just the terms of the sequence. So this could go up to infinity, it could go to 5, it could go to a million, it could go to n plus 1. We don't really know what it's going to. So obviously we have no idea what this last number could be. Well, we're going to find that out. That's what we're going to be using. So the a sub n is called the nth term of the sequence, and the entire sequence is notated using curly brackets. So a sub n, if we use curly brackets here, this will tell me that it is a sequence. Okay? So let's do some examples. First example, list the terms of the sequence. And list the terms, it doesn't really matter, I guess, how many we do. I mean, we want to do a couple. We don't want to do like 2. So if I say a sub 1, okay, when, right, n is equal to 1, n equals 1, we're going to get 3 plus negative 1 to the first power, which is just 2, right? If I say n equals 2, which is a sub 2, then I'm going to plug 2 into n, and I'm going to get 3 plus negative 1 squared, and that's going to be 1 plus 1 is 4, right? A sub 3 is going to be 3 plus negative 1 to the third equals, and that's 2. Okay, and I'm going to keep going, and hopefully you can see a pattern here. If I go to the fourth, I'm going to get 4 again. And you can see the pattern, right? There's a dot, dot, dot there because we're going to always be either positive 2 or positive 4. And that's going to help us determine some different things later on. In number 2, okay, if I want to find the first couple, we're going to say, okay, a sub 1 is equal to 1 over 2. A sub 2 is equal to 1 over 4, right? A sub 3 is equal to 1 over 8. 1 over 16, right? 1 over 32, 1 over whatever. And this sequence, okay, this one here is actually going to, remember in the last unit we talked about converging. This is going to converge to 0 at a sub n. So a sub n is going to be about 0, okay? A sub n is going to be about 0 because of just how big the bottom is getting, but how the same, like the numerator is always going to be 1, right? And then this one here is a little bit confusing, but we need to kind of understand what this is going on. This is called a recursive sequence, because in order to find the next number, we have to use the previous value. Okay, we have to use the previous value. So this is defined by previous terms. The number before will determine what the next value is. So like this one really didn't, like this 1/2 didn't help me with the next sequence, right? Or the next term in the sequence. I just got the next number, a 1, 2, 3, and these numbers were based on that number that I put in. Whereas here, this is going to, this right here is going to help me determine what the next value is going to be. So if I say, so since D1 is 25, okay, D1 is 25, I want to find D2. Well, if that's 1 plus 1, which is equal to D1 minus 5, so this is D sub 2 is equal to 25 minus 5, which is 20. So D sub 2 is 20. So now I want to find D sub 3. Well, d sub 3 is really what? 2 plus 1. So that's d sub 2 minus 5, which is 20 minus 5, which is 15. And then d sub 4 is equal to d sub 3 minus 5, which is going to be 10. And I keep going in that direction. Okay, so d sub 1 is 25, d sub 2 is 20, d sub 3 is 15, d sub 4, I don't know why that's not a d, that should be a d. D sub 4 is 10, and d sub 5 would be 5, right? And keep going in that order. So the 10, or this number, or this number, whatever the previous term is, it helps us determining what the next term is. That's called recursive. A primary focus of this chapter concerns sequences whose terms approach limiting values. So we talked about that in the last unit when we had the limit as some value approaches maybe infinity of an integral, right? And whatever this was, dx or dy, dt, whatever the heck it was. And we said if this is equal to some number, okay, then it means it converges to that number, okay? If it is equal to infinity, then it diverges, right? And that's what we're going to be dealing with here. And so, for instance, this sequence right here, we talked about this up here, it converges to 0 because the denominator gets really, really large and the numerator stays as 1. So when I divide a number 1 divided by a really large number, it's going to get to 0. And so how do I do this? I take the limit as n approaches infinity to determine whether, and if it is going to converge, to what value a sequence converges. Okay, let's do some examples, and we're going to use well, this one here is the same first one from up there, so we can show that that is not going to diverge, or that is not going to converge, is going to diverge. Okay, so we're going to take the limit as n approaches infinity, okay, of the function 3, or of the sequence, I guess, 3 plus negative 1 to the n. All right, and we're going to be able to see that from our work above, this was either going to be 2 or 4, no matter what. So if n was positive, it's going to be, or if n was even, it's going to be 4. If n is odd, it's going to be 2. And because it doesn't settle on one single number, you can think of it like, so if I have my graph here, it's going to be at 2 or 4, 2 or, well, 2 or 4, 2 or 4, 2 or 4. It's not even going to be lines. Like, it's not going to be any value between 2 and 4. It's just going to be 2 or 4. 2 or 4, all the way to infinity. And so this diverges. Okay, this diverges. So that sequence is going to diverge. Well, this one here, let's look at it. So the limit as n approaches infinity of the function n over 1 minus 2n. So we can use two different things to do this. One is we can plug in infinity, and this is going to go to infinity over infinity, which then we can use L'Hopital's rule, right? We can use L'Hospital's rule, L'Hopital. We can, L'Hopital, okay? We can use that, take the derivative, and I can do limit as n approaches infinity of 1 over negative 2, which then we know that's negative a half, right? So then this is going to converge to negative a half, okay? Well, if we remember, we can use, whenever we have something that looks like this, we can use horizontal asymptotes, right? If we remember. If you don't, that's fine, okay? Make sure you use L'Hopital's rule correctly. We can use horizontal asymptotes and say, if the power on top, or if the top is growing faster than the bottom, then it's going to infinity. Well, in this case, the top and the bottom have the same exponent, so they're growing the same rate, and then I just divide coefficients, right? I just divide coefficients. So negative a half. If the bottom is growing faster than the top, then it's going to go to infinity. Or then it's going to go to 0. It's going to 0. Just like this, 1 over 2 to the n. This is definitely growing faster than the top. So that's why that's going to go to infinity. Okay? Oh my gosh, to 0. What am I doing? It's a long night. It's late. Actually, it's not. It's only 10:15. Let's do the last one here. So, well, not the last one, but number 3. N approaches infinity, okay, of n squared over 2 to the n minus 1. Well, if I use L'Hopital's rule, or if I actually think about, I can use horizontal asymptotes. So let's do horizontal asymptotes in this one to see how it goes. Well, n squared is going to grow really fast. Like, this is going to grow fast, but 2 to the n actually grows significantly faster. Okay? Because if this was, say, 7 squared, right, is only 49. But 2 to the 7th is, I don't even know, it's already in the couple hundreds, right? So obviously that's going to keep growing faster and faster. So because the bottom grows faster, this is actually going to approach 0, so therefore this sequence converges to 0. If you wanted to use L'Hopital's rule, you can, which in this case it'll be actually harder because you have to take the derivative of 2 to the n minus 1. And 2 to the n, if you forgot, is the ln of the base times the original function times the derivative of that exponent, which is 1. So if you forgot that, then maybe L'Hopital's rule isn't for you. Maybe the horizontal asymptotes is for you. So let's look at the fourth one here. Let's take the limit as n approaches infinity of the ln of n over n. Well, what's going to grow faster? Actually, the bottom is going to grow faster. So if you think about what the ln of n looks like, okay, the ln of n kind of looks like this. But the n is actually going to look like this. So this is going to grow faster than the ln of n. So that means using horizontal asymptotes, okay, this is actually going to approach 0. So this converges to 0. If you don't want to use horizontal asymptotes and you want to, do this using another method, let's do L'Hopital's rule, and I'll explain why we do it. If I just plug infinity to the top, the ln of infinity is going to be infinity, and then the bottom is going to be infinity as well. And so because this is indeterminate, I can use L'Hopital's rule. I'm just going to use LH, okay, L'Hopital's rule. And so that means the derivative of the top, which is the ln of n derivative, is 1 over n over 1, which is just 1 over n. Now I can plug infinity, so that's 1 over some infinity, right, which is 0. So that's another way to do it. Okay, remember you have L'Hopital's rule to use. All right, let's do the middle one. So this notation, if you forgot what it was or have never seen it before, this is what we call a factorial. So we're going to do a little bit of background here. A factorial is taking whatever term it is. So if this is n factorial, that's an exclamation point. It's not, in math, it's not an exclamation point. It's considered factorial. So what this means is we're going to take the letter n, we're going to multiply it by every number below it. So n minus 1, n minus 2, n minus 3, all the way up to ... n minus n. Okay, and we're going to multiply all of this stuff out. Well, actually, it's n minus n plus 1. No, n minus n minus 1. Yeah, there we go. So that's what we do, or I can do this and do ... and go 3, 2, 1. I can do that. That's fine. That'll work actually better. So that's what the factorial means. Okay. Well, now I got to think about how this actually works in terms of n plus 1 factorials over n factorials. Okay. So what does the top mean, or how can I rewrite the top? Well, because it's n plus 1 factorial, that means the term n plus 1 is going to be multiplied by n, and then n minus 1, and then n minus 2, ... 3, 2, 1. Okay? So really what's going on is I'm taking the n plus 1, and I'm actually going to multiply n plus 1 by n factorial, because n times n minus 1 times n minus 2 times n minus 3, ... 3, 2, 1 is n factorial. We just talked about it right here. And so I can, if I'm dividing this, those are going to cancel, right? So let's just do the limit here. So I get the limit as n approaches infinity of n plus 1 factorial over n factorial, which is equal to n plus 1. Because the n factorial is going to cancel, right? We just showed that. Okay, so that's equal to just infinity, right? Because if I plug infinity in to n plus 1, I'm going to get this series is going to diverge. Okay, this is going to diverge. And then this one up here, okay, I get n plus 1 factorial over n plus 3 factorial. Well, what does this actually mean again? So the limit as n to infinity of n plus 1 factorial over n plus 3 factorial, this is actually n plus 1 factorial over n plus 3 times n plus 2, n plus 2, make it so we can read it, times n plus 1 factorial. So the n plus 1 factorials are going to cancel, and I'm just left with 1 over n plus 3 times n plus 2. So I'm taking the limit of that as it approaches infinity. Well, that means the bottom is going to grow significantly more than the top, and therefore this is going to approach 0, and so this is going to be converge to 0. Okay, converges to 0. We're going to use it, I believe we're going to use factorials a lot. I know in calc in college and higher level math we use factorials a lot. So we're going to be able to get more practice, hopefully. But we need to really understand what factorials are. So if you have a question, please ask. They are a huge component of series and sequences. All right, let's get on to the second page. Hopefully this doesn't take too long. But these rules look very similar to what you've done before with limits and derivatives and integration, where if the limit as n approaches infinity of some sequence is L, and then the limit as n approaches infinity of some other sequence is K, if I am taking the limit of A plus B, or A of n plus B of n, I can just take L plus or minus K. Like, it makes sense to do that. If I'm multiplying them, then I can multiply the L and the K. If C times some sequence, okay, and then I can say that, well, it's really C times the limit as n approaches infinity of A sub n. And so because this is L, and that's C, then it's C times L, okay? And then if I'm dividing sequences, I can take its L over K, provided that the sequence on the bottom is not equal to 0, and therefore then K is not equal to 0. Otherwise, that you can't do, right? You can't divide by 0. Okay, let's do squeeze theorem, because that's going to be awesome. That's a joke. Squeeze theorem for sequences. Basically, remember the squeeze theorem for limits. Okay, it's very similar to that. If the limit as n approaches infinity of some sequence A sub n, is equal to L, and therefore the limit as n approaches infinity of B sub n is also equal to L, there exists an integer n such that A sub n is less than or equal to C sub n, which is less than or equal to B sub n, for all little n in big N, then the limit as n approaches infinity of C of n equals L. And you're like, I don't get that. That doesn't make any sense. And that's true. Like, that's fine. This is more math speak, right? And so what it's basically saying is that C sub n is being trapped, okay, is being trapped between, I'm going to abbreviate between, A sub n and B sub n. So it's being trapped between A sub n and B sub n. And because it's being trapped, if both limits approach 0, okay, so does C sub n. And what does this mean? Well, if I have a function, okay, so say I have this function here, it's going to go like this, and we're going to call that A sub n. So if I look at this function, like, it kind of looks like it's going to approach 0 or converge to 0 in infinity, right? Converge to 0, all right? If I have a B sub n, which maybe it kind of looks, maybe not like that, maybe kind of like that. If I have a B sub n, that kind of looks like it's also converging to 0. Okay, converge to 0. If I have another function, C sub n, that is kind of being all crazy and doing that, we're going to see that at infinity, this is going to level out. Okay, so this is our C sub n. And because it's being trapped in between the high and A sub n and B sub n, like the high and low sequences there, then we know, using the squeeze theorem for sequences, that C sub n is also going to be approaching 0 because it's trapped in the middle. Trapped in the middle with you. That's a good song, right? I think that's how it goes. So we're going to do that as well for the squeeze theorem. So let's do this down here. Alright, so we're going to show that the sequence C sub n is equal to this. It converges, and we want to find its limit. So what I want to do is I want to start off with my kind of inequality symbols, and I want to make sure C of n is going to go in here. And then my A of sub n and then B sub n are going to go on the side. I'm going to try to start with the function in here, okay, c sub n, and what actually does this function, like there's some things about this function that I know that they're going to be in the middle of. So for instance, let me go back to Squeeze theorem for limits. Okay, back in, I don't know, Calc AB, okay, we talked about Squeeze theorem for limits. So if I had like sine x times e to the x or something like that, we know that we're going to take sine x because that travels between -1 and 1, right? We know that, and then we can multiply by e, right? And then I get negative e to the x, negative e to the x, and positive e to the x, and this is now e to the x as well. And I can figure like, hey, this is what the limit is going to go towards, okay, as it approaches some value, whatever that value is, all right? And so I want to do that here. There's something in this sequence that actually is going to always alternate between something. So I'm going to say, well, it's -1 to the n. Well, -1 to the n is going to alternate between -1 and +1, depending upon the value of n. If n is even, then it's going to be +1. If n is -1, then if n is odd, then it's going to be -1. And so because I chose that little piece, I'm able to say that is going to be between -1 and +1. Then I'm going to multiply everything by 1 over n factorial. So this is -1 over n factorial, this is -1 to the n over n factorial, and this is 1 over n factorial. Okay? And so now what I have to do is I'm going to take the limit of both of these things as it approaches infinity. So I'm going to take the limit as n approaches infinity of -1 over n factorial, and you're going to see this is really -1 over infinity, which is actually equal to 0. And then I'm going to take the limit of this piece here, which is the limit as n approaches infinity of 1 over n factorial, which is equal to 1 over infinity, which is equal to 0. And because both of those functions, a sub n and b sub n, approach 0, we know that the limit as n approaches infinity of -1 to the n times 1 over n factorial is also going to approach 0. And therefore, this converges to 0. Okay, that's how we use the squeeze theorem. We need to be able to find a nice function that we're able to put inside, and so that is going to alternate between values. Okay, and then we just kind of go from there, multiply both sides by what we have remaining, or divide, or whatever we need to do to get our original function c of n in there, or c sub n in there. Okay, let's go down. I want to find the nth term of this sequence. Well, the hard part is I gotta find the sequence. Okay, so I need to find a sequence whose first 5 terms are those 5 terms. And they are not reduced, so it gives you a little bit of an opportunity to find out what those values are. And this is hard if you've not really done kind of anything like this before. But you're going to have to play around. So here's what some strategies to work on. The first, we know it's probably going to be a fraction, right? So because there's a fraction here, it's probably going to be a fraction. So that's one strategy. The next strategy is, well, it alternates, right? It alternates. So because it alternates negative to positive to negative to positive to negative, and probably all the way through, right? We know we're going to have some -1 in there. And if n is 1, so if n was 1, that's negative first, right? So that means that this is going to be n. If it was positive, then this would be an n minus 1, because then -1 to the 0 would be positive, and that's why we got to make sure, we got to check our positive and negatives out. Make sure it aligns correctly. So this is -1 to the n. Well, let's look at our denominator. Our numbers are 1, 2, 6, 24, 120. And again, if you've never dealt with factorials, then you're going to have a hard time. And this just is n factorial. So this is 1 factorial, 2 factorial, 3 factorial, 4, and then 5, and then 6 and 7. 6 factorial is actually going to be 120. Oh, I'm sorry, 720. And then 7 factorial is going to be, I don't even know, 40, no, 50, 40, actually. Once you get good at them, you'll be like, oh, actually, that makes sense. Like, once you start doing them, the numbers are going to be in your head, and you're like, oh, that's 4 factorial. You're going to be like a nerd walking down the street, like, you're going to see, like, the number 24, and you'll be like, whoa, that's 4 factorial, let's go. No, I'm just kidding, that won't happen. But anyway, so the bottom is going to be n factorial. How do I get the numbers on top, regardless of the negatives or positives? Okay, so let's think about this. Well, I have the number 2 here, the number 8, 26, 80, 242. I can kind of think that, well, maybe it's a power of 2, because they're all even, right? Maybe they're powers of 2. So, like, what about 2 to the n? Like, if I made n 1, then that's 2, that's good. If I made n 2, that's 4, but that doesn't give me 8. So we got to kind of play around a little bit. And in reality, it's going to be 3 to the n minus 1. So 3 to the n is 3. If n is 1, that's 3. Minus 1 is 2, and that's where I get that from. Okay? If it's the second term is 8, so 3 to the 2 is 9. 9 minus 1 is 8. That's how I get that. So we got to play around with numbers. You're going to have to do a lot of stuff in your head, or maybe calculate really quick. But this is our sequence. And so I want to find the 6th term. So I'm going to take a sub 6 is equal to negative 1 to the 6, 3 to the 6 minus 1 over 6 factorial. So that is equal to 728 over 720. And you can leave it like that. That's okay. So what happens? We want to determine if it converges or diverges. Well, what's going to grow faster? Okay, so we got to take the limit as n approaches infinity of the sequence, negative 1 to the n, 3 to the n minus 1 over n factorial. Well, what is going to grow faster? N factorial is actually going to grow a heck of a lot faster than your top. And it starts here, like 720 is obviously smaller than 728, but if I took a to the 7th power, or a sub 7, and I did negative 1 to the 7, 3 to the 7 minus 1 over 7 factorial, like my denominator is already 5040, and I doubt, so that's 729 times 3, that's going to be in the 2700s. So figure 2700, something like that. So that we can definitely see that this is going to keep growing faster, and so this is going to approach 0, so therefore this is going to converge to 0. Okay, that's it for this video, a quick breakdown of sequences. The next couple videos I believe are going to be a little shorter, so that's good, but have fun on this, make sure you do the work, ask questions, and I will see you on the next one. Deuces.